In this lecture, I'm going to create dummy code, and then you're going to see, essentially the idea is to let you see how the different parts of implementing an artificial neural network or a deep learning neural network, how they come together, especially within a Pytorch framework. So we can import Torch. Now I'm going to provide an input layer comprising of a given number of neurons, a hidden layer. So we are just putting together a very simple artificial neural network, and we just have one hidden layer, and the output, which is just going to be 1. And now we are going to initialize the parameters. And essentially we'll have to define, because remember with PyTorch everything is underpinned by tensors, so we define tensors for each parameter of each layer, and we just have one hidden layer. But of course, if we have more than one hidden layers, then we have to define the parameters for all the hidden layers, and essentially we can even do it automatically in PyTorch anyway. So I'm going to, first of all, let me just create the tensors for the input and the output. X torch dot, and that's how we create. I'm just creating a dummy input tensor and an output tensor. One input one output. And we also need tensors for the bias and the weights layer. So I'm going to create a bias for the hidden layer to begin with. Again, the same procedure. And we create a bias for the weights layer. Now the first thing that we do when we implement an artificial neural network or deep neural network, the first thing is forward propagation. So let's just do forward propagation. And what this entails is that we are going to define Z, we are going to assign random weights, because the whole point is that we start by assigning random weights and essentially combining them in a linear fashion. Inputs plus bias, and this is what we pass, and we pass the Z to an activation function, and obviously that is how the neural network proceeds forward. And right now we are just talking about moving forwards. So before going any further, I'll just mention that we also initialize tensor variables for weight. So I have two variables, w1, w2, and in w1 I define the weight of the hidden layer the way I define bias of the hidden layer in b1. Torch.random input hidden, these are the parameters over here, and then we define the weight of the output layer like so. Now we are going to define a sigmoid activation function using Pytorch, and I'm defining sigmoid because sigmoid, as you know, is a very commonly used activation function. So I create a custom made function by calling the keyword def sigmoid activation. I pass in Z because essentially it is this Z that we pass into the activation function, and it can be any activation function, and we are going to return this. Now we are going to concentrate on the part about carrying out the activation. So the first, let us just define the activation of the hidden layer. And then we are going to define activation of the output layer. And before I do that, we'll actually define the activation. So we are going to pass this Z1 into the activation, the sigmoid activation function I defined earlier. And we define the activation of the output layer. At torch.mm I can carry out the multiplication between my inputs and the weights, or rather in this case A1. Because it is this A1 which will be passed on here, and then we need the output which will be obtained after it has been passed through an activation layer, the sigmoid activation layer. Loss. we'll just define the loss very simply. The predicted output will be subtracted from the actual output, which is y. So y minus the predicted. So now we come to the step of backpropagation, and I know I spent a lot of time talking through the theory and showing some extremely complicated mathematics to you, but the upshot about backpropagation is that it seeks to minimize the error in the output layer by making changes to the bias and weights, and these changes are computed using the derivatives of the error term. And how we do the derivatives, I've discussed that, but it's unlikely that you'd ever have to compute those derivatives by hand. So let me just define that. Now we are going to compute the derivative of the error term. And remember, the derivative of the error terms, they're defined in terms of delta. So delta O for the, this is going to be the error term for the output. Error term for output. Delta for the, now this is the error term for the hidden layer, and this is supposed to be sigmoid delta. So once we compute the deltas, we are going to backpass the changes to the previous layers. So D output loss into delta output, loss H, torch D output, W 2T. And essentially this is how we start moving the error backwards through our neural networks. And when we do that, we update the parameters, and that is where alpha or learning rate comes in. And indeed we can specify any value of the learning rate, and there are no hard and fast rules, and this is something that in practical terms we play around with when we build our actual neural networks. And then we will finally update the biases and the weights, the W1 and the W2, using this particular learning rate. And this is an iterative process, and we typically run this code many times or through many epochs before we finally are able to get the lowest possible errors and adjust our weights and bias in such a way to get the lowest possible errors and the highest possible accuracy. And this is just a toy code, but it just shows you that how things like forward propagation, back propagation, and updation actually come together in any artificial neural network, not just Pytorch. And these are the steps that we can implement through the different deep learning packages out there, including Pytorch.